All right, so this again is the Hardy-Weinberg law that describes the expected frequency of genotypes given allele frequencies. And so let's see how we can use the Hardy-Weinberg law. So firstly, what I just want to reiterate here is that this allows us to be able to do two things. Firstly, we can calculate, one, the allele frequencies in the current generation, knowing the genotype frequencies. So we saw that in our initial example. Similarly, we can calculate the genotype frequencies in the next generation. From the allele frequencies in the current generation. And this turns out to be a very powerful relationship. So let's take an example of how we could use that. So let's consider the Irish population. So in Ireland, there is a high frequency of the autosomal recessive disease cystic fibrosis. It's a disease we've encountered, and we know it's autosomal recessive. It occurs when you have two carrier parents. Okay, and the frequency, I will just erase this here. So the frequency of cystic fibrosis in the Irish population is, in the Irish, 3 out of 10,000 births is the frequency of cystic fibrosis, okay? And so that is equal to a frequency of 0.03% of births the child is affected with cystic fibrosis. And so we know the genotype for cystic fibrosis, so we can figure out, we know this information here tells us what the frequency of the CFTR mutant, CFTR homozygous mutant genotype is in the Irish population is 0.0003. Of course, we have to divide by 100 to get here. So we've added 2 zeros, so that's correct. Okay, and in fact, now using this relationship up here, we know that this is our Q squared genotype frequency, and so let's put that here. Okay, so given that we know that the current genotype frequency in the Irish population is our Q squared, or 0.0003, we can ask, what is the allele frequency? What is the allele frequency? And to do that, what do we need to do? We need to determine Q, which of course we just take the square root of our Q squared. And so that's going to be the square root of 0.0003. And that turns out to be 0.01732 is the frequency of the cystic fibrosis disease allele in the Irish population, which we can compute knowing the genotype frequency, which we've just got from epidemiological data, knowing how frequently we get affected cystic fibrosis children in the Irish population. And of course, when we know Q, we know P. We get it for free. And so P is going to be equal to 1 minus Q. And so that's 1 minus 0.01732, which is equal to 0.983. And so P in this case is the wild type, or the non-disease causing cystic fibrosis or CFTR allele. Okay, and so we can ask a very important question here now. We can ask, what is the frequency of carriers of the cystic fibrosis disease allele in the Irish population. And so let's determine what that is. What is the frequency of carriers? Carriers, in this case, are the heterozygotes. And so, of course, looking over here at Hardy-Weinberg, we can see that to calculate the frequency, the expected frequency of the heterozygotes, it's simply 2pq. We calculated q over here and p, and we have those allele frequencies over here. So let's do that simple calculation. 2 times 0.01732 multiplied by 0.983. And if we do the math, that equals 0.034. So remember, this is our frequency of carriers. And the carriers, in this case, are the CFTR mutant, CFTR wild-type individuals. And so this is our frequency. If we want to get it to a percent, we can multiply by 100%, which is equal to 3.4%. And so what this tells us, given the frequencies, the allele frequencies in the population, is that the frequency of carriers in the Irish population is 3.4%. And so this is an interesting illustration because the frequency of affected individuals is very low, 0.03%, but the frequency of carriers is actually very high, 3.4%. That's a large fraction of the population are carriers of that disease. And so this sort of illustrates the point that when an allele was rare in the population, most of those alleles, those rare alleles, are present in the heterozygotes. And so a problem that I'd like you now to work on at home by yourself is, given that we know the frequency of carriers in the Irish population, if you were going to be doing genetic counseling for some prospective parents and you had 2 Irish parents, what would be the probability that they would have an affected child? And that's something that you can compute directly from these numbers and your knowledge of Mendelian genetics.